Hello, welcome again. Let us continue with the basic concepts of engineering thermodynamics. At the end of this session, we will you will be able to define thermodynamic work and heat, and you will be able to compare and contrast work and heat. First, what is this thermodynamic work? We have been defining work in physics. What way this thermodynamic work is different? In physics, when we define, or in mechanics, when we define work, we say work is force into distance traveled. Unit of force is Newton, unit of distance is meter. The work done is so many Newton meter. If you look at this animation, look here, I am lifting a book of 10 Newton weight for a distance of 1 meter. What is the work done? 10 Newton meter. So that is the definition. So we say that W is equal to integral of 1 to 2 f dx. If f is constant, we can take out and integrate dx. We'll get the length and we can get the work done. So what is the problem? Why we have to define thermodynamic work in a little different way? From this definition, it is clear that work will be performed only when the system changes the position, that is when the process is performed. Please note here, there are many cases in which neither the force nor the displacement of point of application of the force are visible. To circumvent such cases, the mechanics definition of work needs redefining for thermodynamic systems. So, this is the idea. That is why we are introducing a very generic concept to define the work, that is thermodynamic work. So, what is the definition of thermodynamic work then? So, we define work is performed by a system on its surroundings during a given process if the sole effect external to the system could be reduced to the rise of a weight and is given by the product of the prescribed weight and the distance traveled by it. So that is how we define the work. So now the question is, it means the same. It means the same. Now let us look at this. Suppose I have a battery, a battery I have. Let us say I have an electric bulb here. The resistance of the bulb, I have shown it as a resistor. Okay, this is the bulb here. Moment I close the switch, current will pass through this and the light will glow. Here, you must clearly understand that work is a boundary phenomenon. That's why we use the word work interaction. It is always an interaction between the system and its surroundings. So here let me put a boundary over here. In this case, if I ask you a question, what is the work done in this case? You say, which is the force, which is the displacement to compute the work. Now what exactly we can do? We can remove this bulb. Instead of this bulb, let me connect this to an electric motor. On the motor shaft, let me mount a pulley with a rope wound on it. At the end of the rope, let me put the weight here. Now, once again, when I close the switch, current will flow, motor will start rotating, so the shaft rotates, so the pulley rotates. So at the one end of the rope, I have connected a weight, it lifts the weight. So weight is the force and the distance traveled. You can measure and you can calculate the work done. Here it appears it is very difficult to apply mechanics definition of work and calculate the work done. So we can really simulate in this fashion and we can calculate the work done over here. So that is the reason why the thermodynamic definition of work is necessary. Suppose here I have put the boundary over here. See here the electric current is crossing, getting over here, and you are getting the work done. Because this is the surroundings here. Surroundings is getting benefited. So there is a boundary over here. This is the surroundings over here. In this case, I have put the boundary enclosing everything. And here is the surroundings, and the surroundings is not getting any benefit or loss. So in this case, we say there is no work done. That's why work is a boundary phenomena. Means either the observer or the surrounding should either get a benefit or it should have a loss. Then only we say work has happened. So please remember that work is a boundary phenomena. You should cross across the boundary. If it is not crossing the boundary, then work is not done. Our surroundings neither benefited or not suffered a loss. So you see here, I take this bicycle, I have a pump over here. I am just filling air into this tube. The air inside this cycle pump, if I consider it as a system, this person is working on that. So surroundings are doing the work on the system. If you consider this as a system here, or you can consider this as a system, surroundings are doing work on the system. You are losing your energy. So work is done on the system. So you are losing. It is a negative work. Suppose you are getting some kind of a profit from here, we can consider it as a positive work. So work done on the system by the surroundings is always considered as negative. Work done by the system on the surroundings is always considered as positive. So here you consider a compressor is there. It is sucking air, compressing it to a higher pressure. So work done, we can calculate P dV, right? V1 by Vf. I'll tell you later what exactly is this. Work is done on this. This is a negative work. Work is done by the surroundings on the system. If you consider this as the system, and by supplying the work, I've decreased its volume from here to here, but pressure has increased. That's what exactly a compressor does. So for this compressor to work, I have to give an electric current. So I have to pay for it. So I lost that one. So work is done on the system. It is negative work. Now you consider this one, an engine or whatever it is. If there is a gas, this is a system. If this pressure is very high and temperature is also high, that will exert a force on this piston. The piston will move and I can convert the reciprocating motion into rotary motion, and that rotary motion I can use it for lifting the weight. Here system is doing work on the surroundings. It is a positive work. So please remember the sign convention for work. When work is done by a system on the surroundings, it is taken as positive. For example, work done by a system by a steam turbine is positive. When the work is done on a system by the surroundings, it is taken as negative. Work supplied to run a compressor is considered as negative. I hope it's clear. And now let us look at, already I mentioned, force into distance traveled. The unit of force is Newton, unit of distance is meter, so unit of work is Newton meter. Newton meter is also Joule. So here Newton, the name of the scientist, that's why capital N. Meter is small, Newton meter. It's also equal to 1 Newton meter is also equal to 1 joule. You can also represent by 1 J. J is capital because joule. Joule is the name of the thermodynamicist. So joule. It should be capital. Something like rate of doing work is what you call it as power. So work divided by time is power. So then the unit is joule by time. The unit of time is second. Joule per second is what you call it as watt. Again James watt. So capital W. So how do we, from the definition, from the original definition of the work, suppose if I consider 1 horsepower, if the 75 kg force meter of work is done per second, we call it as 1 horsepower. So 75 kg force meter. I want to convert that into Newton meter. So 1 kg force meter, I have written it as 9.806 Newton or 9.81 approximately. You can write here 9.806 75. Then you will get Newton meter is nothing but joule. Joule per second is nothing but watt. 735.5 watt or 0.7355 kilowatt 1 HP. So sometimes 1 PS is slightly different from 1 HP. You can look into any manuals and what is the PS value we can find out. So 1000 watt is 1 kilowatt. 1 HP is smaller than a kilowatt. So 1 kilowatt is equal to, you can say 1000 divided by 735.5. If you do it approximately, you get 1.36 1.36 HP. 1 kilowatt is approximately equal to 1.36 HP. So what is this PdV work or displacement work? So as I mentioned, work is nothing but force into distance traveled. Force into distance traveled. Let us assume a system is executing a quasi-static process. Assume that initially the piston was here. On this piston, assume that I am keeping a number of very thin slices. So once I take out one slice, this will move a very small distance. Let us call that distance small distance, infinitely small distances, dl. So let me consider some intermediate point here. The piston is here. Now let us say this is the system. Okay, this is the clearance volume. Okay, let me consider this part as the system now. The pressure is P over here, that is acting on the piston. Correct. So moment initially the piston was here, this edge was here. Moment I take out that infinitesimally small slice, it will move from here to here. That distance, let us say dl. And this piston cross sectional area, it is circular, pi by 4 d square. That cross sectional area into this length, you can call it as infinitesimally small volume, say dv. So work done is force into distance traveled. Force is nothing but the pressure acting on this, and A, the area of cross section of the piston. So PADL. So ADL I call it as dV. So force into work done. So it is an infinitesimally small work done. Let me represent by delta W. I'm using the word this symbol delta because, as I said, work is not a point function, it's a path function. Once again, we'll explain that. So that is the reason why I have represented by delta W. So now the question is, from this end to this end, when I move the piston, I can go on adding this small PDV, 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 PDV instead of that. So I'll get number of such PDVs, but I can represent integral of PDV, but there are infinite number of such PDVs. So that is why I'm using the symbol integral. This is from initial volume to final volume when I move the piston. V1 to V2 and P is the pressure and dV. This is the infinitesimal small work done. When I integrate, I'll get the work done when I move the piston from point 1 to point 2. Here I'm using the word symbols P and dV. I'm calculating the work done by knowing the pressure and the change in volume. So that's why I call this work as PDV work. Here the piston is moving from one end to other end. There is a displacement happening. I call this work as displacement work. So if I know the values of P, if I know the change in volume, we can always find out what is the work done. So such a work we can call it as PDV work. Work a path function. What we mean by that? Look here, I have initially, you consider, assume that this piston edge was here. So I know P, I know V1. So let me call this pressure as P1 and volume as V1. So I mark P1, I mark V1. I'll get the initial state. Next, let us say the piston moves from this end to this end. When the piston edge is here, once again I'll know the volume. Also I know the pressure. I mark P2 and V2. By chance, while moving the piston from 1 to 2, the system must have followed this path. So let us consider like this. This is station A or station 1, this is station 2. Let us say it is considered as station 1 is, let us say, Bangalore, station 2 is Chennai. I may follow this particular route and reach Chennai, or I may follow this particular route and reach Chennai, or I may follow this particular route and reach Chennai. Probably I am traveling from 1 to 2 through a car, using a car. Probably when I follow this path, the fuel consumed by the car may be different when I follow this route, when I follow this route. The same way, the system is undergoing change of state from state 1 to state 2, maybe by following this path. Other than pressure and the volume, some other property may also be there. I'm changing this kind of thing like that. These values are changing. So if the unit of, since I have drawn this on pressure and volume coordinate system, the unit of pressure is Newton per meter square, pascals. Unit of volume is meter cube. If I multiply these two units, I'll get Newton meter, which is nothing but the unit of work. So that means if I take this curve and draw a vertical line and find out this area, this is what you call it as the work. Work done by the system or done on the system, whatever it is, when it undergoes a change of state from state 1 to state 2, following path C is this much. By chance, if it follows path B, then the work done is this much is the area. So if I follow the path A, then the work done is this much. Please note that the quantity, the work done is depending on, not depending on the end state. It's depending on the path we follow. That's why you can call it as work a path function. And as I mentioned earlier, a path function is not a property of the system. So work is not a property of the system. It is simply a boundary interaction between the system and its surroundings. So the same thing has been explained over here. So please note that work is a path function. Then let us see other types of work. What are the other types of work? One of the types of work is what you call it as the shaft work. What is the power transmitted by a shaft, or what is the work transmitted by a shaft? Assume here I have a shaft. At the end of the shaft, I have mounted a pulley. I am applying a force tangential to this. That force is, let us say, Ft. When I apply a force tangentially to this will have a displacement. When I apply a force Ft, let us say the angular displacement is d theta. Angular displacement is d theta. If r is the radius of this, then this length is r d theta. So this is the force and the displacement is r d theta. So then we can say the small amount of work done, say delta Ws, is equal to Ft r d theta. You know, earlier I have told force into radius, I have defined it as torque. That is what torque, torque d theta. Correct? Now if I divide by time, then I'll get small work done divided by time. If I do it, I'll get rate of work done is nothing but power. So d theta by dt is nothing but, this is angular displacement. D theta by dt is nothing but angular velocity, which I represent by omega. You know, velocity is rate of change of displacement. In linear case, we write dl by dt. Then that becomes velocity. Here d theta by dt. Then this is angular velocity omega. What is omega? Omega is nothing but 2 pi n. Suppose one rotation means one rotation of this, it will cover 2 pi radians. If it is making n revolutions per minute, then it will cover a total angular displacement of 2 pi n. If I divide by 60, I will get n by 60 will become number of revolutions per second. So now let me substitute for omega over here. Then the shaft work or the power transmitted will become 2 pi nt by 60 watts. It should be capital W, right? So W 2 pi nt by 60. That's how we say. It is very, very useful in mechanical engineering because we design many machine components, and all that time we use large number of shafts there, and it is necessary we have to design the shaft for different machineries, and this is very important. So what is the work power transmitted by a shaft? It is what is the work done per minute, force into distance, you can say. So average torque, that is finally from here it comes average torque into angular displacement. Then you can write T 2 pi n by 60, then it will become 2 pi nt by 60 watts. This should be capital W. So P, this is nothing but omega, so T into omega. So omega is nothing but 2 pi n by 60. Suppose you are designing a gearbox, let us say. This is a driving shaft, that is the engine shaft. This will be driving a counter shaft. These gears will be driving the main shaft. This will transmit the power. This will transmit the power. This will transmit the power. While designing the size of these shafts, it is necessary to have this knowledge. So what is the shaft work? Or power transmitted by shaft is this thing. Power transmitted is 2 pi nt by 60, or power is equal to T into omega. Correct. Now let us look at stirring work. I have just taken an insulated chamber. There is a fluid inside. If I go on stirring, the fluid temperature will increase. So that means I use a stirrer like this. What is the work done on the system? Work done on the system. Suppose at the end of the shaft, I just wind a rope like this. At the end of this rope, I'll just connect it to a weight. If you allow the weight to fall down or move down, this will rotate automatically, it will stop. Since I know this weight and the distance traveled, I can always find what is the work done. That work is what we call it as stirring work. So weight is nothing but mg, the displacement dz. So small delta will be mg dz, we can call it. Correct? This can also be called as this force into this radius. We can also call it as torque, and there will be an angular displacement d theta. So T d theta. From here you can calculate that. So if I sum all these things, small works and all those things, I'll be getting mg dz integral 1 to 2. So this is what you can find out. 1 to 2. This is mg dz. We can write it as integral of T d theta. Correct? This is the work done for small these things and all the displacements. Choose right. Find out these things. This mg is nothing but weight. So this is weight. This is not work. Don't mistake it for work. This work into the weight into dz. That's the meaning of that. Okay. So we can calculate what is the stirring work. Similarly, when current passes through a bulb, so you'll get the light. So this is the resistance. So what is the electric work here? Actually, you cannot find out what is the force, what is the displacement, but it is always possible to use this electric current to raise the weight. So what is the electrical work done in this case? Current is nothing but rate of change of charge. So I can say dc by dt. What is the potential difference that I am applying across this? Let us say E. What is the work done? E into charge flow. So E into dc. What is dc? dc is nothing but I dt. So what is the work done in this case? Integral of ei dt. Okay. So this is what you can say. So now if I work by time is power. Power is nothing but ei. So ei joules. This you can represent. This is the electric power. What is the electric work? You can always say EIT, just where T is the time. Or in this case, I have used the symbol tau. Tau is the time. Suppose what is the work done in stretching a wire? Look here, I have a wire. I'll apply weight here. I'll stretch this wire. So such a work again using fundamentals. Force is nothing but stress into area. Force by area is stress. So from this equation, again, stress by strain is Young's modulus. So you can replace sigma by E into epsilon. What is epsilon? Epsilon is nothing but strain. What is strain? Rate of change of length. So please look into all these things. Finally, we can find out what is the work done. Here, work is done on the system, considering wire as a system. A epsilon L by 2, epsilon to final strain, right? Epsilon 2 square minus epsilon 1 square. So if you know the area of cross section of the wire, strain, correct, initial strain, average strain, sorry, length of the wire, if you know those kind of a thing, it is possible to find out these things, right? Look here, when you have water in a container or any liquid in a container, something like that, the molecules of the liquid which are on the surface, they experience surface tension. Surface of any liquid behaves as though it is covered by a stretched membrane. You see here, this molecule is pulling this molecule is pulling, this molecule is pulling like this. It is under some kind of tension, surface tension. So because of that, you know, the film gets stretched. Area of a surface film, right, changes. So what is the work done then? Work done is, again, you see here, this is sigma surface tension, which is given by Newton per meter, correct, multiplied by change in area. Then you can find out what is the surface tension. What is the change in area? You multiply it by surface tension, then you will be getting that initial area and final area. If you know, we can find out this. What is the work done? This is what we call it as work done in changing the area of a surface film. If you apply mechanics definition, maybe it's quite difficult to compute that work. Suppose when you magnetize an iron piece, what is the work done for magnetization? You see here, you are applying a magnetic field H and allowing the current to pass through it, and you are magnetizing it. Then what is the work done? It is nothing but magnetic field strength multiplied by the current that is passing through this. So thus we can find out all this works using these equations. There is another very important interaction, is the heat interaction. Look here, I have a boiler or a container filled with some water. Now if I start supplying heat by burning a fuel or whatever it is, this water gets converted into vapor. It becomes a steam. If I make this vapor enter into a steam engine, and I can produce the work output. So again, if I can put a boundary around this kind of a thing like this is a boundary phenomenon, heat interaction. So heat is an interaction between the system or between a system and its surroundings, which occurs by virtue of temperature difference when they communicate. Already we have defined temperature, which is a consequence of zeroth law. This is at a lower temperature, this is at a higher temperature. Because of this temperature difference, the heat will cross the boundary and enter into the system. Okay, so just like work is also a boundary phenomena, it is, again, it has a sign convention. Suppose you are supplying heat from its surroundings to the system, this we call it as the positive. The other way, it is negative. So heat supplied to the system is positive, heat lost by the system is negative. It is opposite to work. Work is done on the system is negative, work done by the system is positive. I think there is some mistake over here. This should have been plus, this should have been minus. Please correct. I'll correct this in the PDF slides. Please make a correction here. The unit of heat is also joule. In MK system, you use calorie. If we can convert 1 calorie of heat is equal to 4.187 joules. So 1 kilowatt hour is equivalent to 860 kilocalories. So this kind of conversion I have shown in the beginning of this course. So you can look at that. So 1 kilowatt hour is equal to, so whole thing what you have to understand, heat is something, a boundary phenomena. Boundary is an interaction. Heat will flow from high temperature region to low temperature region because of low temperature region. And heat, like work, is also a path function. Instead of, let us say, P and V coordinates, I draw it some other coordinates. I represent this coordinate as temperature, this coordinate as, let us say, entropy, which I'll explain later. And if I substitute the units of these and multiply, that will become the unit of heat, nothing but joule. Suppose the system initially it was state 1. Let us say the same system was at state 1. After supplying the heat, it will come to, say, let us say state 2. I might supply the heat in such a way the system will change the state like this. Follow this path to undergo the change of state. Then this area is the amount of heat that I have supplied in this case. If at all it follows this path, then this is the amount of heat that is supplied. If I follow this path, this is the amount. So it all depends on the path, not on the end state. That's why heat is also a path function. Since heat is a path function, I represent small change in it as delta Q. I use indefinite integral. So this total integration value we represent it as 1 Q2 not Q2 minus Q1, which is true for definite integral. So that's how we are representing, and very clear, since it is a path function, it is also not a property of the system. It is simply a boundary phenomenon. So what are the similarities between heat and work? As I mentioned, both are boundary phenomena. Neither work nor heat are the properties of the system. Both are transient phenomena and exist whenever system executes a process. Heat and work are not something which are possessed by the system, hence they are not the properties of the system. Both are path functions and therefore form the inexact differentials. Hence they are not thermodynamic properties. Hope I have clarified the definitions connected with thermodynamic work and heat, and we have also compared work and heat. Thank you very much. We will meet again in the next video. Thank you.